So basically, this is a strange talk about strategy in physics research, really. I'm going to give you my usual speech. Of course, my end point is that what I'm doing is the right strategy, but I'll try, instead of just saying it, to motivate it for once. And I need you to take, for the purpose of this talk, as working assumption, just for 40 minutes, that the objective of physics research is not to get citations or go on TV, but is actually to discover new physical phenomena. Okay? So in this I need, crucially, because this is now winning. Okay? So we win when we discover a new physical phenomenon. And our game then is to maximize the probability that our work leads to discovery of a new physical phenomenon. Now, it's a very simple, evident fact that we maximize this probability of winning if we have a good theoretical idea and somebody makes an experiment that confirms that theoretical idea. That's the standard path. But in other areas of research, it's not equally important to appreciate that this is really our winning probability is really the product of the probability that our idea is good and the probability that our idea leads to a prediction that can be tested experimentally. In other areas of physics, in most areas of physics, I guess, if your idea is good, basically you win. Because it will produce a prediction, chances are testable. So, let's say our students are trained to think that the objective of physics research is to have good ideas. And this is sadly wrong. The objective of physics is not to have good ideas, but to maximize our winning probability. And in quantum gravity, I mean, the two things are indistinguishable in, say, some areas of condensed matter research. The two concepts are indistinguishable, and the first one is more romantic. You win if you have a good idea. You win if you understand, quote unquote, how the universe is. But in quantum gravity, problem is that the second probability is relevant, which in other areas one could say is roughly 100%. So you make a prediction. Most things predictable in a given area of research are measurable. In this field, as you well know, is the biggest problem of this field. You have lots of predictions that we cannot test. And so for many predictions, for many potentially good idea, I mean, P-theory is always very small anyway, however smart you think you are. P-theory is always very small. It can be, if you have 10% on P-theory, you are great. I guess Higgs said maybe, well, in the 60s he had maybe 5%, but 5 years ago he probably had 80%. That's it's incredibly high P-theory. Okay. But the problem we have is that we have very low P-theory, that's fine, but even lower P-experiment, typically, often zero, basically. Most good ideas, I repeat, good idea doesn't mean I would never dream one of you, or especially me, to be smart enough to have good idea that means P-theory is 100%. But I think good idea means P-theory is 5%, 10%, something like this. And that some of you, not me, are smart enough to have such a good idea, PTH of 10%. But chances are, if you have such a smart idea, then your P-experimental is 0%. Not because it's not destiny, it's not evil. It's just that very few things can be measured with the precision that this area of research requires. So there is probably a change of culture about the objective and the strategy of physics research that this area is bringing about, and that perhaps our students should be prepared very young. I mean, I'm condemned, but young people could start thinking of physics from the very beginning in this term of a game you want to win. And now we go to the title of my talk, which Jurek got wrong twice, which is very good. So I like to think of this exercise of maximizing the probability of winning as the needed preparation for being lucky, actually. And it's a good, I think, a useful mindset. And my title is a tribute to a book which is very nice, which I think should be one of the textbooks of first-year physics, which is Ace on the River. And this book is very elegantly written, but also very sharply explains how the career of a super strong poker player was dramatically changed by a very lucky instance. So he got the right card at the right moment. But the book, if you read it all, you also understand how much preparation and careful use of logics was required for him to be ready to be that lucky. And for those who understand the game, an ace on the river can change quite a bit in your life at the right time. So, over the last 15 years, has been growing effort of research which either consciously, more often subconsciously, is adopting this strategy. So we don't measure a theoretical idea in this area that I'm here representing. We don't measure a theoretical idea only on the standards of, the compellingness, whatever that means, the subjective compellingness of the idea, but we try to factor in also, again, a subjective assessment, but an educated subjective assessment of the chances that this proposal might lead to testing, to successful testing. And the field became big enough that now there is a review that actually I hope I'll have the strength to update next year. It's a big review because there are many more or less wild ideas that are being pursued as possible pictures for quantum gravity which have an associated hope for testing in some areas of physics that goes from precision atomic interferometry measurements to the stuff I'll discuss here, to cosmology, and there is a whole large area now that is being looked at in this way. Probably my second main claim today is that, however, my assessment is that still now, this was more obvious 15 years ago when this was the first idea that made had a little success in the community, but even now, my claim is that our among these research programs that are out there that follow these logics, the one for which my subjective estimate, but I think is shareable, of that maximizes our winning probability is in the area of, in the rather vague and large area, somewhere in the area of departures from our currently adopted relativistic laws. And it's very easy to understand why this could be the case from the side of P-experimental, as I call it, because some relativistic laws are the laws we test better in physics. And relevant to this subject and talk is the fact that, for example, we expect to test in the foreseeable future the wavelength independence of the speed of massless particles. It could be neutrinos, actually, as I will stress later, or not necessarily photons, possibly with precision of 1 part in 10 to the 30. Okay. And certain kinematical thresholds for particle production mainly those relevant for cosmic ray physics, in an appropriate sense provide accuracy to some relativistic laws, testing the relativistic laws, to better than 1 part in 10 to 20. So it's very obvious that such a strong symmetry, anyway, tests of 0 are our best tests anyway, for obvious reasons, and in particular, the omnipresence of relativity is such that we have particularly strong limits on its predictions. Now, to go back to my main point anyway, this P experimental, now, it would be wrong, it would be the other side of being wrong to be all excited about this P experimental being pretty good in the sense that I just described, if then we should assess if our inevitably subjective but hopefully educated assessment, P theory was 0. Of course, you can have P experimental as high as you want. If P theory is 0, you have no chance of winning. It looks to me, and subjective assessment, which I hope a few people, well, it looks like a few people share, is that instead P theory is not so bad in this area of, well, not worse, it's surely small, but not worse than most P theories I've seen in quantum gravity research for this idea of departures from currently adopted relativistic laws. There is no way to know P theory. You can kind of compute P experimental if you give a sufficiently quantified definition, but P theory is anyway just your guts, really, anyway, unless your logic is faulty, in which case it's a different story. It's worth noticing that as we realized more and more clearly over these 15 years, space-time non-commutativity, which has some motivation for quantum gravity research, pretty often, I would say nearly inevitably, leads to some departures, more or less strong, which is important for phenomenology, of course, if they're strong or weak. But it's a good point to stress that space-time non-commutativity nearly inevitably produces some implications on relativistic observables. And since I'm here and I love Kappa-Minkowski, let me stress that still the best toy laboratory for these kind of considerations is Kappa-Minkowski, which is strongly linked to this institute. Jerzy is not here. No. So I didn't need to kiss his ass, but it was okay. But it was honest. You can tell him that I like to do it when it's true. Then we have 3D quantum gravity. We now understand it really well, I guess. From very different perspective, we get to the same results. So that's when I start feeling that we understand it well. And 3D quantum gravity probably has little to do with 4D quantum gravity. We all know that it's not standard dimensional reduction, but it has, surely it does have on the more than on the quantitative, on the conceptual level, it shares quite a few of the features of the problem of interest for the quantum gravity. And there we have now rigorous results. Relativistic symmetries are deformed, and blah, blah, blah. You all know that. So this clearly must add a little bit to our PTH. There are some followers. I'm not sure I can estimate how many, but there are some followers, and not very few, of the Orava-Lifshitz proposal in the quantum gravity community. Those followers should add something to my PTH, because Lorentz symmetry is strongly affected in that picture. And my feeling is that perhaps the most exciting result for reassessing positively for once PTH in this area is the fact that there is more and more spreading of results on dynamical dimensional reduction in a variety of quantum gravity models. And gradually we are also understanding that this dynamical dimensional reduction nearly inevitably leads to at least some consequences for relativistic laws. So I would say few other ideas in physics have a PTH comparable to this. But I mean, even if they have PTH 10 times bigger than this, my claim is that no other idea in physics has P experimental 1/10 of this. And that's what and it's the product I care about, winning. Now, as a little update on the relevant phenomenology of a more standard style, let me advertise also for self-promotional reasons that this simple idea, which is kind of related in a little bit to the previous talk, it's also here very important that the Planck length disappears. So maybe it's some of you who have looked at the paper, but not from that perspective. We probably did not stress enough how important it is for our ability to obtain some result with the relative locality framework, the fact that the Planck length goes away in the h bar going to zero limit, and we are left with m Planck there. That's the crucial point, and it looks like all that m Planck could do if you send h bar and g Newton to zero. So you switch off quantum mechanics and gravity in principle, but you keep the ratio fixed so that m Planck is not zero. It really seems like there's nothing else that this physics, this regime of physics could do but to have a curved momentum space. So I advertise that from that point of view. I also advertise that, again, if you curve momentum space, there are inevitable consequences for relativistic laws, the softest of which are my preferred type, the DSR relativistic type. So laws where you still don't have a preferred frame, but the relativistic laws are deformed by the scale of curvature of momentum space. This is easily done in this framework, especially, well, I think only if, but in the compelling case where momentum space is maximally symmetric, then you have space to produce a DSR relativistic framework. And again, in this institute, I should stress that if momentum space is maximally symmetric, if it is a group manifold, then you end up with a Hopf algebra structure for the relativistic laws. Again, this issue being one of the top places for Hopf algebra description of space-time symmetries. But as you have heard, Giovanni, have you already given your talk? No. As you will hear later today, you can also have, and this is very exciting, you can also describe fully relativistic symmetries in terms of something which is not a Lie algebra, is not a Hopf algebra, is something new, something with non-associative laws of products here and there. And I cannot miss ever the opportunity to stress that we already have seen one evolution of relativistic laws, of course, from the Galilean laws to the Einsteinian laws. And that evolution took the trivial law of composition of velocities of Galilei into a law of composition of velocities that, if you study it in full generality, is non-associative and non-commutative. So for the only relativistic evolution we have met so far, a composition law which is non-associative and non-commutative played a role, and that's why I'm particularly excited about the developments that Giovanni, I hope, will mention later today. I'm not going that far. I'm not going that far for this audience, but as a, you know, maybe for you and I, I think general covariance on momentum space is undesirable, but we can agree to disagree happily on this and keep discussing it. But so I'm discussing with a fixed frame on momentum space. What matters to me most is that this, with this curved momentum space picture and the relative locality mindset behind it, we also have a way to do these computations, to produce predictions for experimentalists in a much more reliable way than the endless arguments that I was involved in years ago. Now, we actually, one of the most elegant, or I like it anyway, results that this curved momentum space picture gave us is that we now understand that those calculations which led effectively to a wavelength-dependent speed of massless particles already 15 years ago, at least in this framework, they are usefully described as dual redshift. They are just redshift, okay? And it's just redshift on momentum space. So just like, as you know, redshift on space-time, when space-time is curved, so redshift produced by space-time curvature, among many things, is also such that if you emit particles, two particles with the same energy from a given source, usual redshift gives you the result that if you emit particles with the same energy at different time from the same source, then they reach the detector at different energy. And one can follow the duality very precisely. The most explicit result was actually done mostly by Leonardo Barcaroli, Giulia Gubitosi, and Niccolò Loré. And follow the analogy, the duality, very guided by the duality, you do the calculation, and you find that momentum space redshift is what causes particles emitted simultaneously, but with different energy from a given source, to reach the detector at different time. So this brings us back with new insight on what was probably the first idea that made a little bit broke some boundaries, at least in a small community, and is the fact that anyway, one way or another, we arrive in some frameworks with low PTH but non-zero to predicting that the time of flight of massless particles from a source to a detector might have a tiny wavelength dependence. Crucial will be this power n. And this, for example, in the curved momentum space picture, it depends on how you curve momentum space, and on some of those coordinate issues, you know, and so those I'm not absolutely not downplaying them. I just advertised my concern that if we have general covariance of momentum space, we are left with no universe. But then what? And so, but so n is crucial for the phenomenologies. If n is 1, actually, we will know soon. If n is 1, and this is because you can test it with photons, and it was realized soon after, well, immediately after, it was understood that gamma ray bursts were typically of cosmological, at cosmological distances. It was easy to figure out that if you put in the numbers, you see that you would have within reach testing this kind of law with n equal 1. We actually, after 15 years, we are probably at the point where the data have the quality to give us this feedback. But we still don't understand, because that duality, for example, that I mentioned earlier, I should have stressed that duality is understood, precise, even simple, if you have on one side curved space-time with flat momentum space, and on the other side curved momentum space with flat space-time. So we understand dual redshift, the effect that here would be tested, very well when space-time is flat. The problem is that if you want to use, of course, these are small effects. The reason why we needed gamma ray burst is for such a small effect to be observable, such a kind of effective velocity difference. So such a small effective velocity difference to be observable, you need very long propagation times. So we needed certain type of source very far away. And very far away means you cannot assume, not even as a starting, you know, as a preliminary, not even as an ordered zero approximation, that the particles propagate in flat space-time. And so, and it is difficult. There is recent work. Also, with Giacomo Rosati, we tried, and we have some picture, and other authors are trying, and this is only a subset, to understand what happens when both space-time and momentum space are curved. Which anyway, again, we are in Max Saborna Plaza, and I should pay as usual tribute to the fact that in 1938 Max Born had this very, I hope, brilliant intuition that in order to solve the quantum gravity problem you needed to preserve his much dear Born reciprocity, you needed to have curved momentum space and curved space-time to coexist. We are at the point where some of us, those working in this game, we are taking that Born attitude. And it's very difficult, however, to understand how they interface with each other, curved space-time and curved momentum space. I think from a phenomenologist, maybe not from a pure theorist viewpoint, but from a phenomenologist viewpoint, I want to advertise this recent work where I think on a phenomenologist level, we at least spelled out and parameterized all our ignorance. So we set the playing field for this game of taking data, assuming that both space-time and momentum space are curved. Many things are left on the theory side. What you see in all publications on this field, when you see about limits, when you read about limits on these kind of effects in this field, so far they're all being based on this heuristic formula, compelling heuristic formula, first introduced by Jacob and Piran, that won the competition of others similar heuristic formula, not on the theoretical level. It just made sense to experimentalists, especially to astrophysicists, and it became adopted. Okay, and what perhaps is on the theory side, the biggest merit of this recent result is that we now understand why astrophysicists were so comfortable with this heuristic proposal by Jacob and Piran. What was behind the proposal is the assumption that, well, something is clearly happening to relativistic symmetries, but nothing is happening to translations. In order to the Jacob and Piran formula to apply, you need a framework where, say, the Planck scale does something, let's say, to the Lorentz sector, if you just to have some way to identify it, but does nothing, absolutely nothing to translations, which may well be the case in the correct quantum gravity, but is clearly not representative of the class of models we are studying. For example, indeed, Kappa-Minkowski, again, playing home here, playing on home field here. Kappa-Minkowski, we know, is a quantum space-time where the scale of non-commutativity affects, in some sense, at the same level, the Lorentz sector and translations. So the Jacob-Piran formula would not apply there. But this is on the interpretation of data. This puzzle about how to put together curved momentum space and curved space-time will play a role in the interpretation of data, in translating data into reliable experimental bounds on parameters. But the quality of data, I don't need, thankfully, this is science, I don't need much to characterize. And for example, when I say that already now we have accuracy of 1 part in 10 to 20 in studies of, roughly 1 part in 10 to 20 for tests of this kind of wavelength dependence of the speed of massless particles, is because these arrival times, you see, this is the arrival time, this is all the highest energy part of a burst, of a gamma ray burst, a burst of photons, and there were thousands, but I'm just showing you something like the top 30, top 25 photons observed, and the time with respect to trigger. You see, trigger was here. Here some low energy photons were already observed, but the high energy part of the signal starts here, and you see just this part. And what is striking is that after a journey of about 7 billion years, this 31 GeV photon was detected in coincidence with the highest, the most intense part of the high energy signal of this burst. So modulo some conspiracies which are possible but unlikely, and of course can be ruled out by observing more and more such bursts. On a single burst you could even consider the possibility of conspiracy, but hopefully we will observe more and more. And if this kind of pictures repeat itself, we will know that we have quality of data such that on 7 billion years journey, a 30 GeV particle remains within a very small fraction of a second of where the main burst. So that the time delay hypothesis is ruled out to the precision, which you need theory to translate into limits on a parameter. But the precision the data give you is the precision of 30 GeV energy difference, roughly speaking, 29 maybe, 30 GeV for a journey of 7 billion years and fractions of a second. This is a burst observed by Fermi in May of 2009. It's a pity Fermi observed in the first year of operation. This is a mystery I have to publicize always. Fermi observed in the first year of operation 5 bursts, 4 more nearly as beautiful as this one. This is the most beautiful and the one that's easiest. Beautiful in the sense of this message. I like to describe it. Every country, Italy has these airplanes, military airplanes that fly in the sky and they stay always close to each other, and it's beautiful to watch them. Well, photons are like those for 7 billion years, and they arrive here with this precision. So it's wonderful. This, what I call beauty is, in this context, is this fantastic, wonderful thing of nature. And they caught 4 more such bursts in their first year of operation. Now it's 5 years more of data, and there is none. So I think there is to be some concern about what's going on with the Fermi telescope. All this story about the conspiracy that I just made should be excluded now. I should have, if not 6, 3 of these. And of course, if I see these on 3 such bursts, the conspiracy theorists will be in difficulty. With 1, and we should have more, but Fermi is somehow either unlucky or having problems. This is to kind of giving you a sense of why I claim that P experimental for testing departures from currently adopted relativistic laws is in some cases as big as 10 to 20, 10 to 22, 1 part in 10 to 20. P experimental it means that P experimental is 100% for certain models. For example, for the case n equal 1, okay? To go back to the logics I proposed at the beginning, for the case n equal 1 in the dual redshift law, for the case n equal 1, P experimental is 100%. The theory is very small. I mean, all this mumbo jumbo about take h bar to 0 together with g Newton to 0, you're left with Planck, then momentum space must be curved. Maybe it's PTH of 1%. And I'm the one who wrote with Lee and the others the paper. This means it's a very good idea, I think. It's one of the best ideas, at least I've had. And PTH is 1%, maybe 2%, whatever. But P experimental is 100% if n is equal 1. And I don't think there is any other idea around which has, therefore, 2% winning probability in this community. But I'm happy to be proven wrong, actually, first of all. And anyway, to discuss it. Things would look even better, opening a wider window of opportunity, if the new observational window of neutrinos we finally have robust evidence that we are seeing some cosmological neutrinos. And as you see described now, the type of data analysis you need to do is somewhat complicated, because you don't expect to, you're lucky if you catch one neutrino from a gamma ray burst. Two, wow, would be fantastic. But we can observe neutrinos up to arbitrarily high energy, roughly speaking. It depends how high are the energies produced at the source. If gamma ray bursts are sources of cosmic ray, of the ultra energy cosmic rays, they are shooting at us also neutrinos of a million TeV, 10 to 18 electron volt. Whether we will ever catch one such neutrino is has to be seen, but if we do catch such a beast, it would bring within reach also the n equal 2. If you have this power n that I was stressing, n equal 1 is, presently I can claim P experimental is 100%, and I don't take any argument on that. For n equal 2, P experimental could be 0, because I don't have any, in order for me to claim it's different from 0, I have to see a tangible way to measure it. And very much this will depend on how the neutrino story evolves. Right now, quite surprisingly, a lot of astrophysical pictures are in trouble for this. It was strongly expected that at this point IceCube would have observed neutrinos from gamma ray burst, but the latest analysis confirms that they're unable to identify any of their neutrinos as a gamma ray burst neutrino. So something is not going well with the astrophysical models behind this expectation for IceCube, and something is not going my way this way. So nature is not cooperating much for the type of game I like to play. Julia, have you talked about the cosmology? I was not. Joao is talking now about cosmology, so I can skip this slide and make Chairman happy. But this will be my last slide. Maybe Joao will stress much more insightfully many of the cosmology implications. What I just want to stress as a side remark to what Joao will say is that what is exciting to me, or what Joao will tell you, is that in some cases we have a picture where there are both implications for astrophysics, which are observable, so P experimental is non-zero in astrophysics. And what Joao will tell you in the language of this talk is that P experimental is non-zero also in cosmology for the same model. This is very exciting to me, because actually having two ways, that would be a way to understand, how much we have to trust the model, if there was ever any confirmation. But in some sense, even, these models have, anyway, very low PTH. But it's conceptually very important that we start to have models which have predictions, testable predictions in very different areas of physics. This shows that this quantum gravity phenomenology really could become slowly like other areas of phenomenology. In other areas of phenomenology, you're not so happy if you just get one prediction right. You actually would like more than one, and from different areas of physics. And to close on a lighter note, I promise it's the last time for those who have seen this joke already twice. After this speech about winning probability, the natural question is, how long will it take to be lucky? We are preparing. The guys who are doing this thing, at least in their mind, at least I convince myself that I'm preparing to be lucky. How long will it take? Of course, we don't know, because the other ingredient for being lucky, in addition to being prepared for being lucky, is luck. And that is not under our control. it's like when you prepare to take a perfect snapshot, and you never know when it will come. I have one from the building next to Perimetry Institute, actually, which is the Canadian Clay and Glass Gallery, where this quite lucky shot was taken. And you would never know how long you have to wait for such a lucky shot to come. Thank you for your patience.
We have time for a few questions.
So can you tell me, just from your point of view, what would be the problem for you if we have general covariance in momentum space like we have in this meta string formulation? Or why would that?
Oh, that's such a long. We have to spend a couple of afternoons on the blackboard.
But just give me.
I mean, general covariance
Yeah.
is such that you have fewer things to observe. Okay, and I can have it on one side. Actually, if I was just coming into this universe, I could equally imagine that I had general covariance on momentum space or on space-time and have a big universe where lots of stuff happens. But if I have general covariance on both sides, my intuition, operationally, I'm unable to define many things. That's my side.
They will be non-local.
Huh?
They are fundamentally non-local.
Yeah, in momentum space and in space-time. They have to be non-local in momentum space.
Totally.
And you lose a lot of observables that we have. But I mean, but anyway, it's unfair that I don't want to use the position of a speaker. All I'm saying is that my concerns are on a strictly operationalist level. I find that conceptually it would be nice to have all this symmetry, blah, 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 but operationally I find myself without the tools to define energy. That I see at the LHC in a calorimeter is something, that energy. And I have problems going on an operational level if I have all this much general covariance.
Yeah, I have a, so the first thing about the beginning of your talk, but you are not saying that citations are not, fair citations are not important, right? Because that's the basic rule of science. I think without that we are dead, no? I know that some people say, oh, citations are not important, and I think that's bullshit.
No. Citations are an important tool, for example, for those who have to evaluate which research to fund.
Right, exactly.
But they don't create science. Well, I mean, it was a very philosophical.
Well, yeah, but I mean,
citations are important in science because some science must be funded, some other science must not be funded, and you need that.
Yeah, but to get there, you need to give a fair credit. Otherwise, you will never get there. Right?
Absolutely. That's what I'm saying. Fair credit, part of fair credit is to give more funding to those who have.
Yeah. But
well,
right.
You know,
even before you make to this panel of funding decisions, I mean
yes. So I was not.
Yeah, no, I'm not talking about the number of citations. That's okay. I mean, you may have a brilliant idea, but I'm not working on it. Then it's okay if I'm not citing it because I'm not. But I'm talking about the fair. Whenever you cite something, it should be fairly, right? I mean, when you do, that's what I'm saying. I'm not talking about
absolutely. No, this absolutely, but it's a different level of what I'm talking. Right. I mean, but you can do research. What I'm saying is that something which is pathological, and you know we have that you do research for the citations.
Of course.
Some people, I've done it in some stages of my career. So first, at some younger stage of my career, I've done it. You know, we have all done it, maybe, or some of us are so pure. But that is not science.
Exactly.
So if you look for is prostitution, we all have our price. But if you it's different when you look for science, and I define science as discovery of new phenomena, and that produces citations. That's the healthy. Because then good science is funded.
No, I fully agree with that. I just meant that this P theory will be affected by fairness of citations, inevitably. That's a fact.
Our estimates, I agree.
Otherwise, what will happen is that you probably we all observe this, and part of our community is splitting in clubs, right?
No,
And
absolutely.
then you will have this club system. And then
Well,
you
you're
say-
touching on a point. P theory, I mean, P experimental has some subjective assessment side, but there's some ground on it. P theory, in principle, especially in quantum gravity, we could all say, oh, your theory has PTH of 0.
Yeah, that's-
Nobody could say you're wrong. So a healthy system of feedback. So when citations are feedback on quality, they are important.
right.
They actually help us. Sometimes I read a paper because it's highly cited. That's another fault I have. I notice a paper is highly cited. I say, oh, why is it? You know, is it worth reading? So when citations, if the paper is really good, then, which is not always the case, but when it's really good, that's one way in which citations are very important. But I'm just saying,
No, I understand.
not having them as the objective, but as a corollary to our objective, which is discovering new phenomena.
And let me follow up with physics. So you mentioned this 10 to the 20 experiment. And so how well controlled these people are in the, because you probably have to model the medium, right, that these photons go through.
No,
the medium.
no, it's
You don't?
absolutely relevant because well, if you're thinking of electromagnetic dispersion,
Something like
you
that.
probably
I
think
don't know.
like electromagnetic dispersion. All other forms of dispersions go down like E squared, basically. So for a 30 GeV photon,
Right,
you
of
can
course.
easily see that the
So
dispersion,
they checked it only for high energy ones.
of course.
No,
We
no.
only
I
use,
thought
this
you were
is the
talking
reason
about
why
comparing high
there
with
is
low.
two good reasons to use
that-
high energy
yeah, yeah,
photons.
okay. Then
It's
of
both
course.
because you get rid of electromagnetic
Of course,
dispersion
of course.
and because the effect is
No,
stronger.
of course, of course. So I thought they were comparing with the low energy ones.
No, it's not. By subtraction, you could
okay.
imagine of doing this by subtraction, because we know so
No,
little.
okay.
You have to
I'm-
put yourself at high enough energy that you don't have to subtract.
Yeah, okay.
It must be a test of 0, basically.
All right.
One last question. I think.
Maybe it's a coffee break. I mean, if you take your formula seriously, P theory plus P experiment
Times, hopefully.
times, yeah.
Or sadly.
Yeah, wouldn't you then say that we could argue that we should all do biology or something like that? I mean,
Of course.
there are many experiments there.
Of course. Oh,
That's
yes, I take the point, and it's true what you're saying. But there is a certain. I'm not claiming that if you love what, who will be offended? If you love space-time non-commutativity, so if you really love space-time non-commutativity, and you want to do it, you do it. It's important to understand that way. And of course, we do quantum gravity research in most of the people in this room because that's what we want to study. We don't want to do biology. My little point is that in addition to what you like to do, which is a good criterion, has always been a good criterion, awareness of this issue that I stressed, I think is, we all know about this issue, but it's not enough in our thing. The tradition is, we look at Einstein, he discovered general relativity with this great idea. Now we do the same. No, we have to well understand we cannot do the same. If the same is needed, we will fail. Because if the best idea is whatever, then there will not be data, and we will discover nothing. So we have to hope that the different path. So often, especially young people entering this field, read about Einstein and imagine that they will do the same journey, okay? To think everything clearly, arrive at the maximum picture, then test it and get the Nobel Prize. This will not happen, This is a sure fact. This is going to be much more luck, much more something bumping in our face, if ever. And the most likely, the most likely probability is this thing is untestable, but yes. But of course, this criterion that I give would be dangerous for us. Is funding agencies started to use PTH type pre-experimental, and we go to apply for funds with biologists or with particle physicists, or okay, we are dead because the highest winning probability I can imagine of any idea, if you factor in pre-experimental, I don't think there is any winning probability better than 2%. That's.
Okay, let's thank our speaker again.
Thank you.